Hello everyone, Anna here. We are now going to do the very last of the videos that go with our chapter 12 on neurophysiology. So let's get to it. All right, so real quick, what is a neural pool? So neural pools are when neurons get together and they work together in pretty large groups, although it can be smaller ones. Typically what you're going to see is thousands of neurons all working together. And in fact, we can be even more specific because we're dealing with the brain. And specifically, it's going to be interneurons. Now, you'll remember from a previous lecture, sorry about my phone ringing. You will remember from a previous lecture that we talked about neurons and how these are short little neurons. They are only found in the central nervous system, and their job is processing. All right, they're talking to each other. They are your thinking neurons. Okay, so what all of this means is that you're going to integrate incoming information, okay, and then forward to wherever it needs to go. And you're going to do this while pooling the neurons to get them to work together, okay? Some good examples of where we are using neural pools is to integrate and coordinate things like breathing rhythm or like moving your arms when you walk, okay, so that they're coordinated. All right, let's look at a picture next. All right, in this little picture, what you've got is an input, oops, let's change color. You've got an input neuron. That neuron is going to come in, but notice that it doesn't go to one other little buddy. It can communicate with a lot of different interneurons, okay? So they call the main area where the main communication is occurring the discharge zone. But then you will often have kind of the outskirts where, if necessary, or depending on what it's doing, it might pull in interneurons on the edge. So this is showing you how you're taking one input neuron and having it communicate with several other interneurons. So this group is called a neural pool of neurons, okay? Let's go on. All right, so we've got four major categories of neural circuits. So a neural circuit is describing a pattern of how these neural pools work together. So this is a pattern of communication. Okay. Now you've got the diverging circuit. So that's where you've got one and then it's going to go out to others. Okay. So one nerve, actually, I don't like the way that's saying that. One nerve fiber. Let's just be a little bit more concise in our language. So, one axon talks to several interneurons. Okay. And it might be just a few. It could be hundreds. It could be thousands. It's more likely to be somewhere in that range though, okay? Now, converging is when you've got many and they're all going to come down to one or a few, okay? So many interneurons converge to talk to one interneuron, or it can also be a smaller neural pool. Okay. Reverberating kind of sounds like what it is, okay? So if you think about a reverberating speaker, you basically have something here, it goes down here, and then it comes back, and it goes around, and it talks again. And you basically get this circuit where it's constantly going back and talking to the starting point, okay? So basically, it's got you got it a start point, and then it goes out, but returns to the start point to, I don't know, you could say it could to support or reinforce the signal. Okay? An example would be muscles that are constantly contracting. Not looking at the cardiac muscle. Let's look at the breathing muscles. So your diaphragm muscle needs to be constantly moving in order to breathe in and out. So that would be a good example of a reverberating circuit, is that communication from the brain to the spinal cord to the diaphragm. And then, oh, by the way, I just stopped. So let's send a signal to the brain letting it know it stopped so that it knows to send me another one to start. Okay? Now, parallel after discharge is a little bit more wonky. Okay? So you've got your starting neuron. All right, so the input neuron, it's going to diverge and then go to several, actually I don't know why I'm putting quotes around that, several other synapses. Okay, so the length in each chain has multiple synapses, but eventually everything is going to reconverge at one or a few output neurons. Okay, so the concept of after discharge, that is actually talking about this idea that you've got continued, I don't know, firing or stimulus even after original stimulus stops. Okay. Now, what we're going to do next is go and look at a picture of four of these four that are from the book. All right, the two easy ones I think are diverging and converging. So you've got a start point of one, and then it goes out to many. Converging, you have many that then converge onto the one. Okay, so they're basically kind of like opposites. Reverberating is you've got 1, 2, 3, and 4. And so it goes in this pattern, and it's going to continue to go that way, but it's also going to send another stimulus that goes back to point 1. And it basically reinforces that signal and keeps it going. Okay. Parallel after discharge. So you've got your input neuron. It's going to talk to some buddies over here. Okay. It's also going to have a main pathway. Signal goes this way, signal goes this way, signal goes this way. Oops, sorry, I drew that wrong. What is it doing right here? No, I did do that correctly. Okay. So it's going to go this way. So you got these all coming down. So I've got 3 paths to 1 output. Okay. And then they all come here, and then it goes out. So you can kind of think of this as also a redundancy system. So I got 3 different ways to get to the same output. Okay. All right. So the next thing we're going to look at is the concept of serial and parallel processing. So let's go to another Blackboard page. All right. So with neural processing, you can do it in a line, okay, where it's very, very linear, or you can do it parallel, where you basically have multiple things working next to each other and then all converging, okay? So when you think of these, again, I throw in the idea of linear for serial processing, all right? And you basically have one stimulus that's going to lead typically to one output, okay? Characteristics are that it's very predictable, very linear, only one thing happens at a time. One of the best examples for serial processing are going to be the spinal reflexes, like your knee-jerk reflex, okay? Parallel processing. So parallel, when you think of it, when you've got parallel lines, you've got lines all going next to each other. So basically, I've got multiple pathways, and these are not necessarily fully linear. They could be using after discharge circuits or reverberating circuits in order to reinforce and complicate the thinking processes. So this is where you do complicated thought. Complicated thought, higher mental processing. All right. So an example that we can build on with this serial processing. So let's take this spinal reflex. All right. So the first thing that's going to happen is you step on a goat head. Okay. You're going to have serial processing that is going to trigger the withdrawal reflex of your leg or foot or arm or whatever it is that you're hurting, okay? So it basically goes to your spinal cord and then goes back out to your foot so that you pick your foot up off of the goat head. But the goat head is stuck in your foot and you're probably bleeding all over the place and you're very, very unhappy about this. So next you're gonna do parallel processing. All right, so parallel processing. Now this is gonna be where you basically send a signal to the brain, okay? And it's where you go through multiple processes to decide that you want a Band-Aid, but maybe you should first pull out the thorn. So pull the goat head out, go get a Band-Aid, maybe wash it, maybe be like, I'm in so much pain, I need to go take a ibuprofen. Or maybe it's like, wow, I really need to go out there and make sure no goat heads grow in this area next year. So this is where you do thought. Okay? All right, hold on a second. Let me see what's next. All right, next what I want to talk about is memory and synaptic plasticity. Okay, it's kind of our next little topic, and we're going to talk about memory a little bit more as we go along. It's very, very cursory in this class. We'll talk about memory a little bit more when we do the brain, but it really doesn't get the attention that that it should get. Okay, so the way we think about it, you have this physical basis for memory, okay? So what you want to think about is like how do we track or find the memory in the brain? So is it like real? Is it like a figment? Is it about communications? What is it, okay? And the physical basis, the thing that we look at is the type and pattern of synaptic connections between neurons. So memory is all about which neurons are connecting and talking, okay? How are they modified to either get rid of them or to make transmission easier, okay? This idea of plasticity or synaptic plasticity is talking about how easy or hard is it to make or change these synapses between these interneurons that we are using for memory, okay? And then you've got this idea of synaptic potentiation. It's a long word to write, hold on. Potentiation, okay? So with synaptic potentiation, this is where you increase the ease of transmission or talking across a synapse, okay? So plasticity is how easy is it, and potentiation is are we making it easier or harder, okay? Now in terms of kinds of memory. Okay, we can kind of break that up into 3 different categories. You have immediate memory, okay? You've got kind of an in-between, which is short-term memory, and then you've got long-term memory, okay? All of these are affected by this plasticity and potentiation idea, okay? You need to have that potentiation making synapses happen, or these types of memories don't form or occur, okay? So immediate memory is all about the immediate, okay? So we're talking about a few seconds of recalling something. So for example, when you read, you are looking at a line and you have in your mind that immediate memory of what those words are, okay? This is also, this idea of immediate memory is what gives us this sense of time, the flow of events, the present, all right? How do we feel the present? How are we aware that something is happening in the now, okay? And I like to think of this as kind of an echo in our mind. And again, this echo lasts just a few seconds. We think some of the research, well, what the book is talking about, I don't know how in-depth this is that this is really dependent on those reverberating circuits that we talked about, okay? Now, short-term memory, which we can abbreviate STM, okay? This one is a little bit longer. So we've got like 5 seconds to 2 to 3 hours, okay? I'm going to draw lines right here so I can do this. All right, so it lasts a little bit longer. This is really important for what we call working memory, okay? You're probably not often very aware of your immediate memory. You're probably more often thinking about your short-term memory, okay? So, for example, you're going to look up a phone number on Google Maps because you want to order dinner, and for some reason it's not letting you hit the call now button. So, gosh, my examples are so old I can't use them anymore. And so being able to recall that phone number long enough to put it into your phone would be an example of working memory, okay? Storage for working memory, you're definitely going to be using circuits, and you're going to be basically doing a lot with what is called facilitated synapses, okay? So you're going to get, when we talk about facilitated synapses, we're talking about these reverberating circuits and these parallel after-charged circuits. And they're going to do something that we call tetanic stimulation. And with tetanic stimulation, what you've got is this idea of rapid repeat stimulus. So, for example, if you're trying to memorize a zip code and you say it to yourself 10 times, that would be an example of tetanic stimulation that you can see, where you basically get this repetitive signal or these repetitive words that you say over, and that helps you remember it. Now, if you do it for a little bit, then most likely after a few hours, it will fade. So a really good example for me would be trying to remember student names. So in class, I go around groups and I learn everybody's name, and I'm really good for that class. 2 days later, I get back to class and I can't remember anyone's name. So my tetanic stimulation worked for a couple of hours, but because I wasn't using it more, I lost the names, okay? If I had made cards and put pictures on it and done names and then done flashcards every couple of hours over the next 2 days, I probably would have learned everybody's names because I would have been using repeat stimulation in order to do that. And I somewhat do that over time by trying to remember to say people's names in class and trying to refresh my memory so that eventually it moves from short-term to a longer-term memory, okay? Post-tetanic stimulation is important here, okay? And this is going to be longer, few hours, okay? And this is about maintaining an increase in axonal terminal activity, okay? And again, if you keep it up for a little bit, that's about how long you'll remember. But if you stop doing this, then you're going to lose the memory and it will not move into long-term memory. Okay. All right, let's do a little bit more with our long-term memory. So let's make some space over here. Okay. Long-term memory, this could be a few days, months, years, or even your entire lifetime, okay? There's some parts of the brain that seems to be able to hold memories for longer, certain types of memories. So memories of smell, music tend to be like the last things that people lose. So like if you look at research with Alzheimer's patients who are getting dementia and are slowly forgetting everything, what you will find is that their memory of smell and of music seems to be one of the last things to go. And it's become, because of that, they're actually using it in treatment to help improve these people's qualities of life because they can remember the music from when they were 20 or whatever, okay? So when we are looking at long-term memory, we can kind of divide it up into explicit versus implicit memories, okay? And basically explicit is this idea that you can put it into words, okay? Now you need to think about it in order to remember it, but you can do it. Implicit is more of your unconscious memory, okay? Sometimes people call this a reflexive memory. All right, so this is going to be like your basic motor skills, like being able to ride a bike. This would also be emotional memories, like every time you see a barking dog, you get scared because when you were 2, you got bit by a dog, okay? Or it can be things like every time you smell lemons, you think of your grandmother's house, you know, something like that. An unconscious memory, okay? When we are forming these long-term memories, you are often having to remodel synapses, all right? So that's going to be the formation or changing of them. So this is all about that synaptic plasticity, okay? Your ability to make or change synapses. You can even stimulate new dendrites and axons to form, or axonal branches to form, okay? At other times, so this is one thing that's involved with forming these long-term memories. Another thing that's involved is molecular changes, okay? And this has more to do with the potentiation idea, where you are increasing or improving the ability for neurons to communicate, okay? So this long-term potentiate, I don't like the way I wrote that. Potentiation, I think that's a little bit neater. This area is going to involve NMDA receptors. Now remember I talked about those when we were looking at glutamate, okay? And these are going to be on the dendrites of the postsynaptic neuron. And when these bind to glutamate, okay, you get a stimulus, okay, and they allow more calcium to enter. And then the calcium is then going to act as that second messenger, which is then going to ultimately lead to depolarization, okay, of that particular cell. But the other thing that's going to happen is one of the jobs. So second messengers, lots of different jobs that can happen with second messengers, okay? One of the second messengers that we already looked at when I did that one slide on glutamate neurotransmitters. So one is to increase depolarization, okay? Or hyperpolarization. So look here, actually, let me just erase that. So it's going to increase local potentials, okay? Maybe lead to an action potential, maybe not, okay? Another job that one of these second messengers can do is when this calcium comes in, it can trigger an increase in the number of NMDA receptors, okay? And basically what this will ultimately do is upregulate, move this up, that postsynaptic neuron so that it becomes more sensitive to stimulus, okay? So that it makes it easier for it to happen, thereby increasing the potentiation so that you form a stronger, more reliable connection between two interneurons, which will theoretically result in a long-term memory being held in at that synapse, okay? All right, let's move on to another topic, okay, that's related. How do we forget, okay? All right, when we forget, what's happening is you are losing potentiation or losing synaptic connections. So if it's a short-term memory, all right, you might just be losing some potentiation so things stop stimulating each other. Or you could be actually breaking a synaptic connection between those things. So when we're looking at these long-term losses or depressions of memory, so not like depression like you're sad, depression of stimulus, okay? So what's going to happen is you've got a decrease in the frequency of stimuli. That can cause the potentiation or the synapses to be lost, okay? And part of this is going to be to a reduction in that calcium that you need to create that potentiation between the different neurons so that you have those NMDA receptors that are responding to that, okay? So you lose the stimulus, you have a loss in calcium, okay? And you can also, as you begin to lose the calcium and all of that, you're going to use proteases that chop up, what's eraser? Chop up those extra NMDA receptors or other types of receptors, which is ultimately going to lead to a reduction in the number of receptors, the reduction in the potentiation, so that you basically kind of lose the thought, okay? I think next what we've got going on is a discussion of Alzheimer's and then Parkinson's disease, so let's look at that. All right, so this is just a note slide on Alzheimer's disease that you are welcome to study on your own, okay? I think most of us at this level are pretty familiar with Alzheimer's disease. Some key things that we're seeing is a deficiency of acetylcholine, nerve growth factor. The two things you might be most familiar with in terms of the diagnosis of Alzheimer's is the presence of neurofibrillary tangles and beta amyloid plaques that are building up within the interstitial fluid of the brain. And basically these are toxic and they increase inflammation. Now, there's a little bit of a chicken or egg situation here where they're not entirely sure if you get inflammation and that leads to the tangles and the amyloid plaques, or if you get the tangles and the amyloid plaques and that leads to inflammation. Okay? But a lot of the research is really starting to focus on how to clear out these beta amyloids or halt their production. Okay? I think I've got a picture of this. So here, what you're seeing on this picture is a brain, and what you notice is that you've got bigger gaps here and that the gyri are narrower, so they're not as big and plump looking. Over on this picture, this is probably hard for you to interpret, but you'll just have to trust me, that the cytoskeleton within the cell has become tangled up, and we call these neurofibrillary tangles, so you can see they're staining a little bit darker. And then this would be a clump of broken up beta amyloid plaques that basically kind of look like clotty areas. They aren't clots, but it's kind of like the same idea as what you get with a clot inside of a blood vessel. I think the very last slide is just summarizing Parkinson's disease. And we'll probably talk about this a little bit more when we do the brain because it's interesting. Here, what's interesting about Parkinson's for me is its relationship to the dopamine releasing areas of the brainstem, okay? When the dopamine levels go down, you start to get this excessive activity and you get these involuntary muscle movements. So I think that's kind of interesting. All right, that was the end of neurophysiology. I believe chapter 13 is next, and we'll focus on the spinal cord first and then the spinal nerves. So I'm going to stop the recording now.